So we've covered a lot of material in the first lecture on entropy. We went all the way through entropy change for an ideal gas. Do you remember something like for incompressible substance, change in S is equal to C natural log of T2 over T1? It looks very similar for an ideal gas. Change in S is equal to C sub P natural log of T2 over T1. That looks very familiar, but you have minus R natural log of P2 over P1. So don't forget this term right here, that for an ideal gas, constant specific heats, the entropy change is a function not only of temperature, but it also includes pressure. Pressure affects the entropy change. Okay, we'll start here, and today we'll basically just cover the area under a curve on a TS diagram and some closed system entropy balance problems. Let's start off with just a general question. Could you, for water, determine the change in entropy given state 1 is at this pressure, temperature, state 2 is at this pressure, this temperature? I hope you could, right? This state right here is superheated. This state right here is subcooled or compressed liquid. With a compressed liquid, if you have a compressed liquid table for water, great, you won't have it for refrigerant. But you can maybe, because the pressure is so high, 10 megapascal, you can find that in the compressed liquid table. Otherwise, you'd have to use an approximation that S is approximately equal to S of F at the given temperature, the saturated liquid's entropy, neglecting the effect of pressure. That's an approximation. For this problem, you wouldn't need to use that approximation because you have the table, the compressed liquid table. Go to refrigerant. They have enthalpy and temperature. It's a little bit of a challenge for students, but enthalpy and temperature, could you find entropy at state 1? This temperature is negative 40. Is that cold? Very cold. It's actually a lot of times the first line in that saturated table for the refrigerant. If you went in there, you would find that H of F is 0 at negative 40, and H of G was 222.88 kilojoules per kilogram, indicating that the given H is right in between the two, isn't it? Indicating that the quality at state 1 is equal to a half, 0.5. So that's how you would get the entropy at state 1. S1 would be S of F plus the quality at 1 times S of G minus S of F. Does this make sense? Are you solving problems? Are you reading the textbook? You need to be, please. Otherwise, some of this lecturing will just like, I don't understand what he's talking about, right? But if you're keeping up, it'll make a lot of sense to you. And if it's saturated vapor at the given pressure, you just need to get S of G. So there you go. How about the next problem? Air as an ideal gas. They give us a temperature and a pressure for both of the states. You can use the air tables. Okay, so if you use the air table, there's a line for 290 Kelvin and a line for 600 Kelvin. So S2 minus S1 is equal to S2 naught minus S1 naught minus R natural log of P2 over P1. So straight out of the air table at 600 Kelvin, straight out of the air table at 290 Kelvin. Here you put your 10 bar, here you put the 2 bar, and that's it. What is this R? 8.314 divided by 28.97. So the universal gas constant divided by the molar mass for the air. How about for helium as an ideal gas? How would you solve for the change in S for helium? When you see air, you can think, I could use the air tables, or I could assume constant specific heats. For helium, you say, I can use the helium tables, or I can use constant specific heats. You don't have a choice. There are no helium tables, are there? So you can only assume or only use constant specific heats. And sometimes in this book, you can beat your brains out trying to find in monoatomic gases specific heat. I've covered this before. I'll cover it again when you take Thermo 2 with me, because I don't want to, I'm tired of seeing wrong answers on final exams. Okay? So how do I find? I have to use constant specific heat. So S2 minus S1 is equal to C sub P, natural log of T2 over T1 minus R natural log of P2 over P1. Let's go ahead and replace this R bar and a molar mass of helium. Molar mass of helium is about 4. And how do I get this C sub P? Well, C sub P bar divided by R bar is 5/2. But that's just the same as C sub P divided by R. So you could put 5/2 R, but we already replaced R by R bar divided by the molar mass. So natural log T2 over T1 minus R bar molar mass natural log of P2 over P1. So you can pull the R bar molar mass out. It's a 5.2 natural log of 5.5. Why did I write 5.2? It's 2.5, isn't it? Proof I'm dyslexic and I need, help. No, I'm just human. That's all it proves, that I'm human. Maybe that's why there's a 6-point curve on the exam. You're human. I recognize you're human. How's that? 2.5, isn't it 2.5? Yeah. How many people saw that and said, where did he get 5/2 from, or 5.2 from? Okay, natural log T1, T2 minus 1 times natural log of P2 over P1. And that's about as compact as you could get. All right. What happens if somebody said it's not helium, it's argon? Everything's the same except the molar mass. Everything's the same except the molar mass. Professor, do I get that on the equation sheet? The equation sheet's already too long. True? So let's press forward. The area under the curve on a TS diagram can be interpreted as heat transfer under the special case that it's an internally reversible process. So let's review. How about a PV diagram first and then a TS diagram, and hopefully you see the parallels. So on a pressure volume diagram, let me do a cap V here. It doesn't matter. It could be per unit mass or it could be total volume and total entropy. But we start with state 1, go to state 2. There's a process, 1 to 2. Is there a work? Okay, and that work is the area under the curve. It's the integral PDV. All right, so we recall that F is equal to, oops, not F, W is equal to F dx. dx, come on now. Where did that come from? Work is equal to F dx. Where did that come from? Definition of work. Maybe that's not a definition, but it is. It's from mechanical work. Understanding what is exactly mechanical work, right? If I take and I put an area here and an area there, did I change the work? No, but I can group that XdA or AdX, and that's a dV. What's force per unit area? Pressure. So work, integral FdX or integral PDV. We look over at the temperature entropy diagram, and we have a process from state 1 to state 2. 1 to 2. And we go back and we say, not the definition of mechanical work, but what is the definition of the entropy? What was the definition of entropy? Was it something like change in entropy is equal to del Q over TB if it's internally reversible? Something like this? Okay, so what you do is you say del Q is equal to TB times ds as long as it's int rev, internally reversible. This must be a process from 1 to 2 that's internally reversible. You can't have internal irreversibilities. All right, but if that's true, then when I do the integral, I get Q 1 to 2 is equal to the integral T ds. The area under the curve on a TDS diagram is Q 1 to 2. Just like this was work 1 to 2, this is a visual representation of the heat transfer. Now, because it's limited to only being for internally reversible processes, the textbook, and a lot of textbooks, will have the notation difference that if it's a int rev process, use a solid line. If it's not an internally reversible process, show it as a dashed line on the property diagram. So if you were going from 1 to 2 and it wasn't, put a dashed line, meaning don't interpret the area under that curve as anything significant. It cannot be interpreted as the integral del Q or Q 1 to 2. Let's solve a problem. Water in a piston cylinder assembly undergoes 2 internally reversible processes. So often they tell us, okay, these are the special processes, internally reversible processes. And they're first and then the second, so it's 2 in series. For each process, determine the heat transfer and the work in kilojoules per kilogram. So they're asking for the work, lowercase 1 to 2, and the lowercase 2 to 3. And they're asking for lowercase q 1 to 2 and lowercase q 2 to 3. So they're asking you to compute 4 things, right? For each process, the specific work and the specific heat transfer. That's what you're asked to find. They show you the TS diagram. What is going on between state 1 and 2? Well, it's isentropic. It's constant entropy. S is constant, okay? Isentropic. And so on a TS diagram, it's straight up. S1 is equal to S2. It's straight up. Okay, now from 2 to 3, they say its pressure is equal to a constant. It just is a curve that's going up to the right on the TS diagram along a line of constant pressure. All right. Look at a table. They give us a table for our properties: pressure, temperature, volume, internal energy, enthalpy, entropy. So those are our standard properties that help us fix states, right? At state 1, they'd say its pressure is 100 kilopascal, temperature 100 degrees C, and it is water. Do those 2 properties look to be independent? Sure, they're independent. It's just slightly above saturated vapor at 100 degrees C. Okay? You can go to the table and you can fill out, oh, this is 1.696 meters cubed per kilogram. This is 2506.7 kilojoules per kilogram. This is 2676.2 kilojoules per kilogram. This is 7.3614 kilojoules per kilogram Kelvin. I left off the Kelvin, didn't I? Sorry, typo. Units on S are kilojoules per kilogram Kelvin. True? All right. So state 1 was fixed. Let's take a look. They don't give us anything about state 2. Okay, let's look at state 3. They gave us pressure, 1,000 kilopascal and 400 degrees C. You go, you look it up, it's superheated. It's in the superheated region. 2 independent properties are there, so I can get the other property values. Let me go ahead and do them. 0.3066 for the specific volume, 2957.3 for U, 3263.9 for H, and 7.4651 for S. So really, it's state 2 that's I need to work on now. Okay, so let's try to figure out what 2 properties do I know about state 2. I know pressure. Pressure is constant. Pressure at state 3 is equal to the pressure at state 1. It's 1,000 kilopascal. And the other property? Entropy. Entropy at state 1 is equal to the entropy at state 2. It's 7.3614. Now it's a little bit of a chore. I'm given pressure and entropy. I'd like all these other properties if I need them, okay? Right? If I need to calculate them, then I'll have to calculate them. Let's do this. Without looking these up right now, can I answer some questions about either the work 1 to 2 or the heat transfer Q 1 to 2? Okay, and so what would I do? How would I know something about the heat transfer 1 to 2? Yeah, and so it's internally reversible. The area under the curve is zero. Okay, so here is that one. Do I have to put any units on 0? This is a conceptual, philosophical question. You know, do I have to put kilojoules per kilogram? Is professor going to take off kilojoules per kilogram Kelvin? Is he going to take off points if I don't put units on 0?
Yeah, probably.
You just think I like to take off points. No. Let me ask you this. If somebody says, I want you to travel a distance of 0 feet or 0 miles, is there a difference in the distance you travel if you go 0 feet or 0 miles? Somebody says you don't owe me any money. You owe me $0 or you owe me 0 millions of dollars. Is there any difference? So in this case, it's one of these where you really don't need to put a unit on it because it's 0. And you could put BTUs per pound mole degree R. That's the USCS unit for entropy, right? BTUs per pound mass. Did I say pound mole or pound mass? Okay, I should have said pound mass. BTUs per pound mass degree R. Okay? All right. Now, so that one's done. How are we going to solve for work? How we solve for work? Well, you tell me. First law. That's all you have to do to make me happy. Give me the principle, the roadmap. How are we going to approach this problem? I think now is appropriate time to apply the first law for a closed system undergoing a process from state 1 to state 2. Let's write down that first law equation, see if work 1 to 2 is in it, and then see how we can solve for it. So Q 1 to 2 minus work 1 to 2 is equal to U2 minus U1. I neglect changes kinetic potential energy. Do you like that equation? What term do we already know is 0? 1 to 2, that's right, Q1 to 2. Now, if I knew U1 and U2, so I really do need to go in and I need to fill in these property values here. What I do is I go in and I find out at state 2 that it's in the superheated region, but it's not lying cleanly on a line. So I go to the pressure block, that's 10 bar, the pressure block of 1 MPa, because I know that's the pressure, right? And I look and I have temperature, specific volume, internal energy, enthalpy, and entropy. And the entropy value at 360 degrees C is 7.3349, and the entropy value at 400 degrees C is 7.4651, and lo and behold, the 7.3614 is right in between. So I just have to interpolate. So when I interpolate, I find that the enthalpy, let me not write all the numbers down, I'll give you the results. It's 3196.2. The internal energy is 2904.97. The specific volume is 0.2912, and the temperature is 368. I don't know if I need all those values, I just got them. It's more of just helping you see if you need them, you can get them. All right, now we come back and we say U2 and U1 are known. I just calculated, put them in the table. And so the work 1 to 2, I calculate, and it's equal to negative 398 kilojoules per kilogram. I didn't leave enough room, sorry about that. Negative 398 kilojoules per kilogram. That's work 1 to 2. See how we did it? Now, we have to calculate the work 2 to 3 and the heat transfer 2 to 3. What do you think? Neither of them are 0. That's exactly it, from the basic definition of work. And how did we find that Q was equal to 0? From the definition of entropy, giving us the integral of TdS is Q. Here, go back to the definition of mechanical work, the integral PDV is work. So work 2 to 3 is the integral PDV. Let me put a cap, no, it's a lowercase, specific volume, that's right. Why do we like that? Pressure comes out because it's a constant pressure process. So all it is my 1,000 kilopascals times the change in specific volume. Let me just put V3 minus V2, and you have to chase your units, meters cubed per kilogram. Some people were in my office saying, I don't know why I did so poorly on the exam. Can you please explain to me why I did so poorly on the exam? I said, okay, I'll take a look at it. And I shared with the student may be here, I don't know. I said, 2 things are killing you. Units. You're not converting units correctly. I can point to 3 or 4 problems where that's the only error you made. The next, you're not neat and organized. You're tripping over yourself. Try to be neat and organized. Try to be more neat and more organized than me. Now, it's hard for me to be neat and organized up here because I'm trying to fit it all into this screen without clicking, because I know what happens. If I scroll down on the screen, guess what you now want to see? You want to see the top. What I just strolled away from, true? So I know that I'm trying to fit it in here. Don't set this is what I do in class and lecture, trying to be fast, as the benchmark for neatness. No, 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 no. You need to be neat in your work. People throw away points, units, and they're just not neat. They're not organized. They're not logical. They're disorganized. That's all I can say. The concepts are in your mind, but you got to get the right answer. True? All right. That's probably the same in statics, probably the same in physics, probably the same in chemistry, all these classes, right? The little things kill you. All right. So this work 2 to 3, when I computed it, it came out to be 15.4 kilojoules per kilogram. And then what about the Q 2 to 3? How do we solve for that one? First law for the process 2 to 3, right? Right? So we just write first law. So we have Q 2 to 3 minus work 2 to 3 is equal to U 3 minus U2. We just calculated work. We just got the properties. The only thing unknown is the Q. and the Q2 to 3 comes in at 67.7 kilojoules per kilogram. Any comments, questions on that? Yes.
Would it be possible to do the area under the curve for Q2?
But I don't know if it's a straight line path or if it's belly up or belly down or whatever. So I can't, yeah. If I did know the curve, now what I could do is I could just take this S, that S, assume it's straight line, get the average, do a box, right, like that, and it'd probably be pretty close. But I didn't do it to see if it would be spot on. Okay.
On the test, if it's a solid line, can we assume it is a straight curve?
It all depends. I mean, this is kind of a caricature. I drew this. It's hard for me to draw these things. So,
You know if you're close.
I did not do that to see if I'm close in this. Somebody want to run the numbers? You can.
Within an order of magnitude.
Oh, it'll be within an order of magnitude for sure. It's whether it's to 3 significant digits that I doubt.
But that's multiple choice. I mean, it helps.
Oh, yes. If it's multiple choice, it really helps because I usually put those answers far away, right? But I usually throw in an answer. Let's say if he can't convert and he's off by 1,000, I'll give him that choice. Isn't that bad of me? Isn't that bad of me? Oh, no, it's not. Come on now. Now we need to talk about the Carnot cycle, because the Carnot cycle is simply a sequence of processes, right? Before we get to open systems, the Carnot cycle we can deal with as a sequence of processes for a closed system. Well, what is that Carnot cycle, especially on a PV that's now a new TS diagram? Well, there's really 4 things when somebody says a Carnot cycle. It can be a Carnot power or a Carnot refrigeration. And when I say refrigeration, I'm not trying to separate and make 6 of them, like you could have refrigeration or heat pump, but moving heat or making work. That's the goal of the Carnot cycle. Either you're moving heat for making it cool or moving heat to make it warm. It's either heat pump or refrigeration, or you're trying to make work or power. Now you can have the power cycle with air as an ideal gas or steam. And you can have a refrigeration cycle with refrigerant, that's just like a steam, that's its parallel, but we won't call it steam, we'll call it refrigerant, or air. And this can throw you for a loop. Hopefully you put that straight in your mind. But when you have the steam or refrigerant, things are condensing and evaporating. I have condensing and evaporation going on. Phase change. Air, no phase change. No phase change. It's always an ideal gas. Okay. Now that we have 4 types of cycles, you can remember that each one of them have 4 processes. All of the 4 processes are internally reversible, and you can start, you can start 1 to 2, either one, but adiabatic compression, isothermal expansion, adiabatic expansion, isothermal compression. So you're going between the compression, expansion, and then you have adiabatic isothermal, adiabatic isothermal. That's the pattern. So why do we study the Carnot cycle? It's our benchmark. It's as good as you can get. And so we beat ourselves up studying this idealized cycle that's not realized in practice, but we try to get as close as possible because you can't get any better. It's the best that you can get. If I calculate the thermal efficiency of the Carnot power cycle, right, either for air or for steam, when I go to my actual system, it's going to have a lower or equal to, if it's a perfect reversible power cycle. Similarly, the coefficient of performance, Carnot, it's the best. It's going to be greater than the coefficient of performance of my actual system. And if the system is reversible, then it's equal to. Okay, so let's go ahead and you have to do these one at a time, but see the forest before you get lost in the trees, huh? Let's try to sketch from our previous study of the PV diagram. Let's do air and a power cycle. So here's an isotherm, here's an isotherm, okay? This will be temperature cold, temperature hot. And 1 to 2 is adiabatic compression. 1 to 2 is adiabatic compression. It'll jump to a higher temperature. It'll go from T cold to TH, followed by isothermal expansion down to 3, followed by adiabatic expansion. It'll drop the temperature down to 4, cold, and then go back up. That's idealized. That's a little sketch on a PV diagram. What's it look like on a temperature entropy diagram? And that's the real reason for revisiting the Carnot cycle, is now put it on a temperature entropy diagram. So if we go from 1 to 2, it's going to jump from T cold to T hot, isn't it? Isn't it going to do that jump? And it's adiabatic. No heat transfer, all right? It's internally reversible. Q is 0. It's a straight line, up and down. So it goes just like this. 1 to 2. Now we follow 2 to 3. It's isothermal. It's going to stay hot. It's going to be flat. Curve could go to the right or to the left, but because we're expanding, we're putting energy into it, it stays constant temperature, but it jumps over to here to 3. Now we go adiabatic expansion. Same reason, it goes down to T cold. And it's a box. It's a rectangle. That's what it is on a TS diagram. The Carnot power cycle is a box on a TS diagram. Now, this is for ideal gas. This is a line of constant temperature, TH. This is a line of constant temperature, TC. This is a line of constant entropy, line of constant entropy. All right? Okay. Let's sketch a TS diagram and a PV diagram for a power cycle using steam. Pressure, volume, temperature, entropy using steam. Well, we said that's when you have condensation and evaporation. You have to put it under the dome. Put it under the dome, and you're going to peg states into the corners at the high pressure, which gives us the high temperature. This is a line of constant temperature. That's TH. Okay. So I pegged state 2 and state 3 right there. All right, let's, again, look at the process 2 to 3. It was isothermal expansion at TH. Did I get state 2 to 3 right? Is it isothermal expansion? Yes, the volume is expanding. All right, and it's constant temperature. Now, to go down to state, let's draw the lower temperature isotherm. Something like this, TC. To go from 3 down to 4, it's a solid line because it's internally reversible. There's still some expansion. From 3 to 4, it's still expansion. It's adiabatic expansion. And so 4 is further over to the right. Then you condense back to 1, but you pick 1 where you stop condensing, such that if you go from 1 to 2, the adiabatic compression, you perfectly land right on 2, which is saturated liquid. And there it is. There is the cycle, the Carnot power cycle, using steam as the working fluid. Make sense? All of the heat is brought in at the high temperature. All the heat is rejected at the low temperature. The other ones are adiabatic processes, no heat transfers. All right? Okay, let's try and draw it on a TS diagram. Yes, sir.
I just had a question. So that TVs that represent is information that we see on the TV on top as far as the 2, 3.
Yeah, this is up here is 2, yeah, the same location 2 to 3. It's isothermal expansion in both cases.
That one seems like it's changing pressure.
It is. For the air it is, and for the steam it's not. That's right. But for the steam, I need to have it, all the heat comes in at high temperature. The best way to do that is tuck it under the dome and bring it in there. So I'm boiling it from saturated liquid to saturated vapor from state 2 to 3. Okay, now do I have a dome on the temperature entropy diagram? Do we have a dome like that for the two-phase region? Sure. Is the top of the dome, the top of this dome, is that the, I forgot the name of that point. Critical point, right? Now, what you do is you have to fit it in, and state 2 is saturated liquid, state 3 is saturated vapor at the high temperature, TH. And down here is TC. And so what does the cycle look like? Well, where is state 4? Straight down. And where is state 2? Straight down, 1 is straight down from 2. And so there is, and guess what? It's a box. It's a simple box. We like boxes. We do. It's a box on a TS diagram. So that's what the power cycle looks like. If I wanted to, this is your line of constant temperature. This is your line of constant temperature. It's almost too trivial, right? On a TS diagram, what does a line of constant temperature look like? It's horizontal. But there you go. Let's try to stay on this diagram, and let's talk about a refrigeration or a heat pump cycle. Let's do it with the refrigerant first. Okay, with the refrigerant first. So focus on these bottom 2 curves. What's different? Opposite direction. That's exactly right. Instead of running in this direction, which is clockwise, run the cycle counterclockwise on that diagram. If you do run the cycle counterclockwise on that diagram, what is the direction of QH? It's out. It's out. It's condensing at high temperature. It's condensing, squeezing that fluid and pushing the heat out at high temperature. Instead of absorbing heat at high temperature, it's rejecting heat at high temperature. That's our heat pump. And it's not absorbing heat at low temperature. It's actually, it's absorbing heat at low temperature. It's cooling, right? Not rejecting at low. So that's all you do. You just run it backwards to go from power to refrigeration cycles. Over here, same thing. Run it backwards. Run it backwards. Okay. So you would, if I wanted to redraw it, I hate to scoot down, but let me draw it straight down. Let's say I want to draw a TS diagram for a fluid that's undergoing phase change. And from 1 to 2, what's happening? It's isothermal expansion at the low temperature, T cold. Then from 2 to 3, what's happening? 2 to 3, adiabatic. What's happening? Compression. And the temperature goes from TC to TH. How about 3 to 4? That's isothermal compression at TH. And 4 to 1, adiabatic expansion. And here it goes TH down to TC. All right? Can you analyze now a Carnot, any one of those four? Give me gas, ideal gas. Give me something that's changing phase. Give me a power cycle or a refrigeration cycle. See, you can mix it up. It's really bad for students, good for instructors who make tests. Right? Because a lot of possibilities. Right? So be able to sketch a Carnot power cycle on a PV TS diagram. We were able to fit that in on the previous slide. I was going to use this space for it, as well as the refrigeration. Now let's move to talking about entropy balance for a closed system. Let me derive an equation. Let's just put a property diagram out there. Generic property 2, generic property 1, meaning, it could be a PV, TS, HS, just general, the concept, the property diagram. And we have state 1 here, and we have a state 2 here. And we can go from state 1 to state 2 along a path, let's say A, and then we can return along a path 2 back to 1 along path B. So that makes a cycle, does it not? 1 to 2, 2 back to 1, path A, then B. I chose to draw one of them as dashed lines, and the other is a solid line. I know I changed the color. The color is not significant, but the dashed and the solid mean something. What does the dash mean? Irreversible. What does the solid indicate? Reversible. Internally reversible, so it's reversible. Now, we can apply somebody's inequality. Carnot's inequality, Kelvin's inequality, Clausius's inequality. Ooh, I forgot what Clausius's inequality said. Did it say the integral along a cycle, around a cycle, of, I forgot what it says, del Q over T has to be negative, less than or equal to 0, and we turned it into an equality, the inequality. We always say Clausius's inequality, then we write it as an equality. Did you notice that? A minus sigma of the cycle. How many people like that? Couple? All right. Now, what was this sigma of the cycle equal to if both A and B were reversible? 0. And so why would sigma not be equal to 0? It's because there are irreversibilities present, right? So because of irreversibilities, for this cycle, it's not equal to 0. Okay. Can I write this cyclic integral as the integral over the path A and then the integral over the path B of del Q over T, del Q over T, and sum them up? True? And so maybe I want to say for path A, it goes from 1 to 2, del Q over T. Okay? Plus the integral from 2 to 1, del Q over T. True? Can I do this, put a minus, and change the limits 1 to 2? Could I do that? Give me a thumbs up if you agree. Right? Is that okay? And then we finish out the equation by negative sigma cycle. Now this one was reversible. This one was just the integral del Q over T. But we had the property, recall, the property entropy. What was the property entropy defined as? S2 minus S1 is equal to the integral of del Q over T int rev from 1 to 2. True or false? That was name calling. I didn't do it. It was done in 1865. I wasn't even born. I'm not responsible. 1865. Think about that. Somebody coined the term entropy. What was his name? Carnot? Clausius? Clausius? Rudolph? Clausius? Right? Yeah, Clausius. So anyway, what I'm going to do is I'm going to replace this by S2 minus S1 right there. Leave this 1 to 2 del Q over T equal to minus sigma cycle. Now the sigma of the cycle really is, I should have done this before, it's only due to A, the path A. There's no irreversibilities in path B, just A. True? Okay, so now let's just rewrite this. We'll have S2 minus S1 is equal to the integral del Q over T from 1 to 2 plus sigma path A 1 to 2. Path A is 1 to 2. And this, guess what? Is an entropy balance statement. We derived it from Clausius's inequality using the definition of entropy for a closed system. It's an entropy balance statement for a closed system. What we do is we can interpret this part of the entropy balance statement as what? Change in entropy. It went up or down. How? Heat transfer. Heat transfer can bring in entropy or can remove entropy. If this Q is positive, right, then it's bringing in entropy. That means heat transfer in, entropy transfer with the heat in. All right. Can T ever be negative? No, it has to be. It's an absolute temperature. That has to be in the definition of entropy is absolute temperature. You'd never have a negative temperature. So, but can del Q right here ever be negative? Yes. That means you can have entropy transfer out of the system with the heat that's transferring out of the system. Okay? Now, this is a plus, and now this term. That was due to irreversibilities. If there are no irreversibilities, it's perfect. That term is 0. If there are irreversibilities, sigma is greater than 0. Can sigma ever be negative? No. T can never be negative. Temperature can never be negative. Sigma can never be negative. Q can be positive, 0, or negative. So you have a lot of multiple choice questions coming at you, right? Because you can change it up. You can change it up. Ooh. A closed system undergoes a process in which heat transfer Q occurs, and that heat transfer Q is positive into the system. If it's negative, it's out of the system. At a temperature TB, so here's our temperature TB. For each case, determine if the entropy change is positive. So is the entropy change greater than 0? Is the entropy change negative, less than 0? Can't write negative. Or is the entropy change equal to 0? Or is the entropy change, I don't know, it's indeterminate. You really can't determine it. Let me pause and let you struggle with a few of these, and then we'll pick it up, okay? All right, so what happens is you just continually apply the equation that delta S is equal to the integral del Q over TB plus sigma, right? Okay, for all of the first 1, 2, 3, 4, they're all internally reversible. What's sigma? So sigma is equal to 0. All the last 3 internal irreversibilities are present. Sigma is greater than 0. Can sigma ever be negative? No, 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 right? So there you go. Now, for the work, no, heat in, that's heat in, right? So this is positive, 0. So what is the change in S? Positive. What about all this work stuff? Complete distraction. Complete distraction. It's irrelevant, right? You know, I gave a test that I gave us information, and I said, and the weight is something, and it didn't need to know the weight, or the color is something, you know. It didn't need to know the color. But the student gets all frustrated. How am I going to use this information? He gave it to me on the exam. It's irrelevant. Ignore it. But it throws them for a loop first time you do that. True? But I think most of life is like that. There's so much irrelevant stuff out there that you just have to ignore it and get to the heart of the issue. In your job, that'll be the same. There's too much noise and irrelevant stuff. Okay, if you have heat transfer that's negative, that's still 0, so it's negative. If it's negative, well, this is a repeat, just changing work, but it doesn't matter, so it's the same answer. And now if you have, it's adiabatic and reversible, guess what? Isentropic is 0. Now that we have sigma greater than 0, if you have heat transfer that's positive, that's adding to it and adding to it, so it's positive. If heat transfer is 0, but you have irreversibilities, positive. You have heat transfer taking some out, but you have some being generated. Is the generation less than removal, or is the generation, you know, what is it? It's indeterminate. You really can't tell. You have to know the relative proportion. One's trying to reduce, one's trying to increase. Right? Oh boy. I got too many problems for today. This problem, if we have time, we'll come back and talk about that problem, okay? Closed system entropy balance. We just derived that equation. It's also known as the second law of thermodynamics. Really? You mean we already got to the second law? That kind of snuck up on us, didn't it? Yep, there it is. Second law of thermodynamics. It says that the change in entropy is equal to the integral del Q over T plus sigma. Does this have to be int rev? No, it doesn't. Basically, if there are irreversibilities, this is non-zero. Okay. What happens if I have multiple heat transfers? Just put a sum, or a lot of times they'll do this. They'll write it like that, sum of the Q1 to 2 over the TB. Meaning, you're assuming the boundary temperature at which the heat transfer is occurring is constant for that heat transfer. And so it's just Q1 to 2, the amount transferred. Let's say I had a problem with this, and it came in, maybe a Q was 100 or 1,000 kilojoules, came in at this temperature of 600 Kelvin, and then there was a Q of 300 kilojoules going out, and a Q of 700 kilojoules going out, and this boundary temperature was 300 Kelvin, and that boundary temperature was 400 Kelvin. So we could do that. We could put in our 1,000 divided by 600, and then the next one would be put in a Q of 300 kilojoules, but it would be a minus because it's out, negative 300 kilojoules, divided by the boundary temperature of 400 Kelvin, etc. So you can write it as a sum as well. You'll see that written that way. Okay. So for a process, that's what the equation looks like. But also, for a differential change, a very small change, you can write it as ds is equal to del Q over T plus del sigma. And it's a small amount of entropy generation. Because entropy is not a property, don't put a D here. Put this delta there, okay? Just like you put the delta there. Q is not a property, so when we have a small transfer, we put delta Q. Entropy is not a property. When we have a small amount of entropy production, we put a delta sigma. And then this is a D because S is a property. But that's our second law written in differential form. Okay. Or for the rate, you say the rate of change of entropy with time is equal to the rate at which heat is flowing in divided by the boundary temperature which it flows in. Maybe I should have put a TB right there as well. Plus the rate at which entropy is being produced. So you have three forms that you'd be familiar with for a process, for an infinitesimal small change, and the rate equation. You'll use all three. Which is most common? I guess the first one for a process. You're good? All right. 2 kilograms of copper are initially at 120 degrees C and cools in a room at 20 degrees C. So here's my chunk of copper. Its temperature initial is 120 degrees C, and there's some cooling until to the room where the room is at 20 degrees C. Let's put T infinity or something like that. What is the final temperature of the copper after it's cooled? 20 degrees C. What equation did you use? Just use your brain, right? If it's going to cool, it's going to finally get into thermal equilibrium, and when things are in thermal equilibrium, they have the same temperature. That's how you conclude that it gets to 20 degrees C. So T2, the final temperature, is 20 degrees C. The initial temperature, T1, is 120 degrees C. What is the entropy change of the copper? I said we had a process, cooling process. Started at state 1, ended at state 2. What is the entropy change of the copper? I pause. I'm going to walk around and see how far you get on that. All right. So sometimes you calculate entropy change by just knowing that it's a property, and so it's mass, specific heat, natural log, T2 over T1. Remember, it is a property. So if you know the end states, you can get the change in the property just by that characteristic, not worrying about the balance or what happened.
That's not the same as equation 6.13, because it has C times the natural log of T2.
Right here is C, specific heat.
Right, but the one on the equation.
I'm using cap S instead of lowercase, and so that's a mass, right? And when I calculate it, it's equal to negative 226 kilojoule point, negative 0.226 kilojoules per Kelvin. Why is it negative? Because it's a decrease. It's going to a lower temperature. The properties lower. If you have entropy's higher for vapors, lower for liquids, lower for solids, and so it's a cooler solid, right? So let me do this. Let's go to part C. What is the entropy generation for an enlarged system so that the boundary temperature is always 20 degrees C? So now I have a large control volume where the boundary temperature is always 20 degrees C. That's 293 Kelvin. True? And I want to know what is the entropy generation for the process of cooling this copper chunk in there. It starts where the copper chunk's 120. At the end of the process, the copper chunk's 20 degrees C, right? So for that system, was there any Q across this boundary? Well, then the air inside of this had to warm up. But the air stays 20 degrees C at the boundary. The air is going to be in equilibrium with the air outside. So the air inside is equal to the air outside. It's equal to the copper inside. It's all 20 degrees C. So was there a heat transfer across the boundary? The copper started hot. It's now cold. Was there a heat transfer out of the copper? The air around the copper started 20 degrees C, ends 20 degrees C. Did it absorb the heat?
Yeah.
So it transferred through that air to the surroundings. Now the surroundings are huge. They're a thermal reservoir. They took whatever heat was transferred to it, but it really didn't change and increase the temperature, right? I went outside and I, exhaled, but I didn't change the temperature of San Antonio today. I rubbed my hands together. I didn't heat up this room. All right? So it's a big thermal reservoir. So was there heat transfer across the boundary of this system, the large system? Yes, there was a heat transfer across that boundary. Now, it was out, which is a negative in. So the Q during the process is a negative so many kilojoules. How many kilojoules is it? How many kilojoules is it that were transferred across the boundary of that system? Well, that copper went from temperature 1 down to temperature 2. The specific heat of the copper, the mass of the copper, that's the change in internal energy of the copper. That's what was the heat transfer out. Look at the first law. Do a first law for that system. What's it say? Q in 1 to 2, I know it's going to be negative. Minus the work 1 to 2, I know that's 0, there's no work, is equal to the mass times U2 minus U1. Right? Did I write the first law correctly? And then we have constant specific heat, so that's mass C T2 minus T1. Well, T2 is lower than T1, so let's switch the order. So we'll put here MC T1 minus T2 equal to negative, and then Q1 to 2. So Q1 to 2 is going to be negative MC delta T, or T1 minus T2. Make sense? Yes or no? Mass, specific heat, T1 minus T2, and that'll have units of kilojoules. So I think, in the interest of time, I'll just say that the amount of heat that's transferred is negative 77 kilojoules. That's the amount of heat that's transferred, I know I'm going to say this, into the system. Because it's negative, it's really out. All right, now, I go to the entropy balance statement. All right? If I do an entropy balance, I have that the final entropy minus initial entropy is equal to the integral of del Q over T. That T is constant, so it just turns into Q1 to 2 over T. The T is constant, boundary temperature of 293 Kelvin, plus sigma. True? I know this. I know this. I just calculated this. I can now calculate the entropy generation for the enlarged system. The entropy generation, sigma, turns out to be 0.0367 kilojoules per Kelvin. That's for the process 1 to 2. Sometimes I'll put a subscript 1, 2 in it. Sometimes you leave the subscript off, just like you sometimes put Q or Q1 to 2. Why was there entropy generation? All it was is copper cooling off in a room. That process is highly irreversible. I'll bring in a room, right? Big room. I'll bring in a 20-degree chunk of copper, and I'll say, you do your magic. You're a smart engineer. Just sit here and turn that copper into 120 degrees C. Take all the energy, from the room, pump it into the copper, and heat it up. and then I'll do the other job. I will solve the problem of bringing in a copper chunk that starts at 120, and I'll do the job of getting it in the room down to 20. I'll just sit there and watch it. I'll sip my coffee and let the process go, right? Where you'll be struggling. How am I going to get that copper to go from 20 to 120? It's irreversible, the cooling through finite temperature difference. Well, you need to work on that. Now, if you really want to challenge, look at part D. Go for a minimal system. Tighten up that system boundary right there. So now the system boundary is tight around the copper. Guess what's changing with time as the copper cools? TB changes with time. You can do the tracking. And what you can find is that the sigma for that process is 0. So it's really not associated with heat coming out of the copper. It's the entropy, the irreversibility is due to the heat transfer from the warm surface of the copper into the cool air. So the entropy generation is in this region in here. That makes sense? All right. Yes.
I have a question. When you wrote the first law and you changed the M times the delta U equal to MC delta T,
Yeah.
I thought that was valid for ideal gases only.
No, solid. This is an incompressible, it's a solid.
Okay, so for any incompressible.
Yeah, and then why didn't you put a C sub P or a C sub B on this, Professor?
Same.
It's the same. But they'll probably put it as a C sub P in the book, in the table in the back of the book. So specific heat of copper, table A19, it's 0.385 kilojoules per kilogram Kelvin. Ready? True or false? I'm going to let you read these and then I'll walk around and see. So, question 1, 2, 3, 4, 5. So, T or F by 1, 2, 3, 4, or 5. All right, you ready to work through it? All right. Proposed process that can be shown to violate the first law of thermodynamics can also be shown to violate the second law of thermodynamics. Why? Two types of perpetual motion machines. One, they make energy, but maybe can't be shown to violate the second law, but they just violate the first law. They make energy. And then the second one is they conserve energy, but they violate the second law. Right? So you have a proposed process.
I guess, right.
Okay. It is possible to have a process that violates the first law of thermodynamics as long as it doesn't violate the second law of thermodynamics. He was outfalsed. His true went, I think I'm not, I want to take back my true. Right? It is possible to have a process that violates the first law of thermodynamics as long as it doesn't violate the second law. No. I mean, if it violates the first law, it's not a good process. It's not going to happen. All right. The entropy of a closed system undergoing a process can only increase if irreversibilities are present. And why? Q can bring in those entropy and increase it. Irreversibilities definitely will increase it, but Q in will also increase the entropy. Entropy is produced in every internally reversible process for a closed system. False. Good. Last one, for an isolated system. What's an isolated system? There's no heat or work transfer with the surroundings. True? It's isolated from the surroundings. Energy must remain constant. Do you like that? Entropy must either remain constant or increase. Could it ever decrease? No. Congratulations. And anybody else that got it? Sorry if I said anybody, like I know somebody's sitting there, hey, I had false, 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 true, and you said it was wrong. Sorry if I did. But I think you were the only one. So otherwise, let's keep going. Ready? Another problem. Let's solve it. An electric motor operates at steady state and draws a current of 10 amps at 120 volts. The output shaft develops a torque of 10 Newton meters and a rotational speed of 1100 RPM. The outer surface of the motor is at 45 degrees C and the surrounding air is at 21 degrees C. Determine the rate of entropy production within the motor. So the motor, we have electric power given amps. Well, let's put, I don't know, different symbols for EMF, electromotive force of 120 volts. And then a shaft rotating at a rotational speed, 1100 RPM. And a torque, T, I think they use that for the symbol of torque in the textbook, of 10 Newton meter. And this temperature right here is 45 degrees C, which is a temperature of 318 Kelvin. So determine the entropy production within the motor. Find sigma, and if you want, you can say MOTOR. So it's entropy production, and it's a rate, isn't it? It's a rate of entropy production in the motor. So sigma dot motor. Good symbol for what we're looking for. How am I going to find it? I pause, I let you work on it. Let's see what you come up with. All right, if you do a first law, energy balance, what do you get? The power that comes in electric, right? Well, first of all, let's clearly define our system. There's the motor. That's our system, okay? So the power is coming in with electric. It's going, I'm going to draw it like this. I'm going to draw Q dot in positive. I know it's not Q dot in positive, but I'm going to draw it Q dot in positive because that's our sign convention in our second law. So we have plus Q dot coming in equal to W shaft going out. Two ins, one out. But the signs will work. When you do the computation, it's voltage times current, and then the shaft, so you find out it's 1200 watts coming in with the electric. It's 1152 watts going out with the shaft. And so Q dot in, I guess I'm going to drop the in, just Q dot, negative 48.083 watts. It's the negative sign I anticipated. It's actually not into the system, but out of the system. Now, when I go to the second law for that system, and I'm going to write what type of equation? For a process or for a small change, infinitesimal process, or for a rate? I do have the rate equation. Let's write the rate equation. The rate of change of entropy in the system with respect to time is equal to the rate at which it's transferring in across a constant boundary temperature plus any entropy generation. Is it operating steady state?
Yes.
And so there's no accumulation or depletion of entropy in the control volume with time. So now we have that sigma dot is equal to negative Q dot over TB. It's equal to a negative of a negative 48.083 watts divided by 318, no, what is it? Yeah, 318 Kelvin. So sigma dot, the motor, I left off that motor subscript, but that's what our system is of. It's of the motor, is 0.151 watts per Kelvin. Those units look good, watts per Kelvin? Sure, they look okay. right? Because it's sigma dot, not sigma. It would be kilojoules or joules per Kelvin. Here it's watts or kilowatts per Kelvin. Now, if you do an enlarged system that includes the motor and the nearby surroundings so that the heat transfer occurs at a boundary temperature that is at 21 degrees C, so the boundary temperature is at 294 Kelvin, you can compute that the rate of entropy production in that enlarged is equal to the same Q divided by a lower T, and it is 0.164 watts per Kelvin. Answer for part B. Which is greater? Why is it greater? What's happening in the air? Heat transfer through a finite temperature difference, where the air close to the motor is hot, the surface motor temperature, and then it's lower temperature farther away. Thumbs up, you like it? It's okay?